Continuing our discussion on isomers, let's look at diastereomers. Diastereomers are a form of configurational isomer, but they do not have mirror images for each other. That's the difference between an enantiomer and a diastereomer. So, these are still stereoisomers, but they are not mirror images of each other. One of the classic examples of a diastereomer are cis and trans isomers. This is cis 1,2-dibromoethene, and this is trans 1,2-dibromoethene. They have the same bond connectivity, so they are stereoisomers. However, they are not mirror images of each other. Therefore, they are diastereomers. Now, you can see here on these couple models, I have the trans version. Let's see here. I have the trans version and here in my left hand now, and the cis version in my right hand. And these model kits show a good, have a good representation because this double bond does not rotate. And that keeps these isomers separate from each other. There are other forms of cis and trans isomers, such as when we have a ring structure. So double bonds can prevent bonds from rotating freely, but rings can too. And so let's look at some example here. So here I have cis 1,3-dibromocyclopentane. There's no double bond in here, but since this is a ring, it's restricting the movement of these bonds. So there can be a cis isomer. And these Hayworth projections are a good way to describe, or see the relationship of cis and trans isomers. So I'll draw the trans isomer. So there's the trans version, and you can see it's on opposite sides of this ring. Now, you may get the impression that diastereomers are cis and trans isomers of each other. And if that were the case, we would just call them cis and trans and not invent another name. There are other diastereomers that are not cis and trans. Now, they're often cis and trans isomers, and that's a good example of them, but They don't have to be. So let's look at an example where they are not cis and trans isomers, but still diastereomers. So at first glance, you may think that these are enantiomers because these molecules are chiral. And they are chiral, but they are not mirror images of each other. Therefore, since they are a stereoisomer and they are not mirror images of each other, these two are diastereomers. And I can show that a little bit clearer with some models here. So here's a model of this molecule right there. And you can see how I've got the methyl group coming out towards us and I have the chlorine going back away from us. And, oh, look at this. Now I'll try to spin this around the right way. I have a model kit of this drawing here. And you can see that I have the chlorine going away from us and I have the methyl group going away from us. So I've matched up the drawing with our model. And if you try to look at both of these at the same time, you can see that the methyl group and everything is a mirror image except this chlorine is going in the same direction, right? And you can see that here on the drawing. It's going in the same direction, going in the same direction. This one's opposite. And because of that, they are no longer mirror images of each other. You can see that the chlorines are going in the same direction. And if this was to be an enantiomer, we would have to move this chlorine over to there in order to make the enantiomer of this one that's up at the top. So these are diastereomers of each other. Now, since they are chiral, we do have an enantiomer for each one of these. So let's draw those and we can talk about what they actually what we have to do in order to get the enantiomer. So to get the enantiomer, we have to invert every chiral center on the molecule. And so here we just inverted one, right? Just the methyl group. If we want the enantiomer of this, we have to invert both. Just like I discussed when we were looking at comparing this one to that one, I said we would have to move the chlorine. Well, we just moved the chlorine to the other side. These right here are enantiomers. We could similarly draw the enantiomer of this structure. And now these two are enantiomers. Now, the relationship between these two, right? Those two and these two, and also in that direction and in this direction are all diastereomer pairs, right? Or diastereomers. They don't have a specific pair. Enantiomers have a specific pair. So left and right and across ways here, these are all diastereomers of each other. But top and bottom here I've drawn, those are enantiomers of each other. That's an enantiomer of each other. So as you can see, there are quite a few isomers that you generate as soon as you start adding stereocenters onto our molecules. And this one had 2 stereocenters, and I've drawn all of the stereoisomers that have the groups in the same position. And so there's 4. Well, if we had just 1 stereocenter, there'd be just 2 isomers. If we have 3, then there are 8 possible stereoisomers. And so the formula for determining how many there are is 2 to the n power. And that is the maximum number of configurational isomers that are possible with n stereocenters. When I say configurational isomers, remember that includes enantiomers and diastereomers. Those are under that umbrella. Now, I say that this is the maximum number because it's possible to have less, and that would occur if we have a meso compound. If you have a meso compound, it could reduce the number of isomers by 1, or if there's a lot of meso compounds, it could be several. So each time you have a meso compound, remember that compound is no longer chiral, and if it's not chiral, it will not have its pair of enantiomer. The other configuration would actually be the same molecule because there's an internal mirror image. So that each meso compound reduces the maximum by 1. So just look out for those. So this is about diastereomers. Cis and trans are examples of diastereomers, but there are other examples that include chiral compounds. Be careful when you're talking about the classification between either a diastereomer or an enantiomer, and the distinction is that if we have inverted all of the stereocenters on the molecule, then they are enantiomers. If we invert less than all, but some of the stereocenters, then the relationship between those two is a diastereomer. So, thank you for joining me for this video, and we'll see you in the next one.